What if we could detect parallel universes? Have you ever wondered what would happen if you made a different choice in your life? What if you took that job offer, or went on that date, or bought that lottery ticket? Would your life be better, worse, or just different? Or have you ever imagined what it would be like to live in a world where dinosaurs never went extinct, or where magic is real, or where aliens have invaded the Earth? These are some of the questions that fascinate us when we think about parallel universes. Parallel universes are hypothetical realities that exist alongside our own, but are inaccessible to us. They could have different physical laws, different histories, different outcomes, or even different versions of ourselves. But how do we know that parallel universes exist? And more importantly, how can we detect them? In this video, we will explore some of the scientific theories that support the idea of multiverses and some of the ways that we could potentially observe them. Let's start with the Big Bang, the event that created our universe about 13.8 billion years ago. According to the standard model of cosmology, the universe began as a tiny, dense, and hot point that rapidly expanded and cooled down, forming the stars, galaxies, and planets that we see today. But what if the Big Bang was not a unique event? What if there were multiple Big Bangs, each creating a different universe? This is the idea behind the theory of eternal inflation, proposed by physicist Alan Guth in 1981. According to this theory, the universe is constantly expanding and creating new bubble universes that are separate from ours. These bubbles could have different physical constants, such as the speed of light, the strength of gravity, or the number of dimensions. Some of these bubbles could be hospitable to life, while others could be barren or chaotic. But how can we detect these bubble universes? One possible way is to look for traces of their collisions in the cosmic microwave background, or CMB. The CMB is the faint afterglow of the Big Bang that fills the entire sky with microwave radiation. It is like a snapshot of the early universe, and it contains tiny fluctuations that reveal information about its structure and evolution. If two bubble universes collided in the past, they could have left a distinctive imprint on the CMB, such as a circular pattern or a hotspot. Several experiments have been conducted to search for these signatures, such as the Planck satellite, the BICEP 2 telescope, and the WMAP probe. So far, no conclusive evidence has been found, but the search continues. Another way to detect parallel universes is to use quantum mechanics, the branch of physics that describes the behavior of subatomic particles, such as electrons, photons, and quarks. Quantum mechanics is notoriously weird and counterintuitive, and it leads to some bizarre phenomena, such as superposition, entanglement, and tunneling. One of the most puzzling aspects of quantum mechanics is the uncertainty principle, which states that we cannot measure the exact position and momentum of a particle at the same time. The more we know about one, the less we know about the other. This means that the particle exists in a state of probability until we observe it and collapse it into a definite state. But what happens to the other possible states? Do they disappear, or do they continue to exist in some other reality? This is the question that inspired the many worlds interpretation proposed by physicist Hugh Everett in 1957. According to this interpretation, every time a quantum event happens, the universe splits into multiple branches, each with a different outcome. For example, when you flip a coin, the universe splits into two branches, one where the coin lands on heads, and one where it lands on tails. In each branch, you see a different result, but you are unaware of the other branch. This process happens constantly, creating a vast number of parallel worlds that are inaccessible to us. In some of these worlds, you could be rich, famous, or dead. In others, you could be living in a completely different timeline, where history took a different turn. But how can we detect these parallel worlds? One possible way is to use quantum computers, devices that use quantum bits, or qubits, to perform calculations. Unlike classical bits, which can only store a value of 0 or 1, qubits can store a superposition of both values until they are measured. This allows quantum computers to perform multiple operations at once and solve problems that are impossible for classical computers. But where does the extra computing power come from? According to some physicists, such as David Deutsch and Seth Lloyd, quantum computers could be tapping into the resources of parallel worlds and exchanging information with them. If this is true, then quantum computers could be a gateway to the multiverse and a way to communicate with our other selves. Another way to detect parallel universes is to use the concept of infinite space. According to some cosmologists, such as Max Tegmark and Brian Greene, the universe is infinite and contains infinite copies of everything, including ourselves. This is based on the assumption that the universe is flat, homogeneous, and isotropic, meaning that it has the same shape, density, and temperature everywhere. If the universe is infinite, then it follows that there are only a finite number of ways that matter can be arranged in a given volume of space. This means that if we travel far enough, we will eventually encounter another region of space that is identical to ours, or at least very similar. In other words, we will find another Earth, or another version of ourselves. But how far do we have to travel to find these duplicates? According to some estimates, the nearest identical copy of you could be about 10 circumflex 10 circumflex 29 meters away, which is about 10 circumflex 10 circumflex 22 light years. That is a huge distance, far beyond the observable universe, which is about 93 billion light years across. To put it in perspective, if you could travel at the speed of light, it would take you longer than the age of the universe to reach your twin. But what if you don't want to travel that far? What if there is a shortcut to another universe? This is the idea behind the theory of wormholes, hypothetical tunnels in spacetime that connect distant or different regions of the universe. Wormholes are predicted by the theory of general relativity, which describes how gravity affects the shape of space and time. According to this theory, massive objects such as stars, planets, or black holes can warp the fabric of space and time around them, creating curves or bends. If the curvature is strong enough, it could create a bridge between 2 points in space and time, allowing faster than light travel. This bridge is what we call a wormhole. But how can we detect wormholes? One possible way is to look for their gravitational effects on the surrounding matter and light. For example, a wormhole could act as a lens, bending and magnifying the light from a distant source, such as a star or a galaxy. This could create a distinctive pattern, such as a ring or an arc, that we could observe with telescopes. Another way is to look for their signatures in the CMB, such as anomalies or distortions, that could indicate the presence of a wormhole in the early universe. Finally, another way to detect parallel universes is to use the idea of a mirror image universe. According to this theory, there is a hidden sector of particles and forces that mirror our own, but interact very weakly with us. This hidden sector could have its own atoms, molecules, stars, planets, and even life forms that are invisible to us, except for their gravity. But what if there is a way to reveal this mirror universe? This is the idea behind the experiment conducted by a team of physicists at the Oak Ridge National Laboratory in Tennessee in 2019. The experiment involved firing a beam of neutrons at a wall and measuring how many of them passed through. The wall was made of a material that blocks most neutrons, but not all of them. Some of them could decay into protons and escape the wall. But what if some of them escaped the wall in a different way? What if some of them crossed over to the mirror universe and became mirror neutrons? And what if some of them crossed back to our universe and became regular neutrons again? This would create a discrepancy in the number of neutrons detected and a signal of a mirror universe. The experiment ran for a year, and the results were inconclusive. The team did not find any evidence of a mirror universe, but they did not rule it out either. They plan to repeat the experiment with more sensitivity and precision and hope to find a definitive answer. So, what if we could detect parallel universes? What would that mean for us, and for our understanding of reality? How would that affect our sense of free will, identity, and morality? Would we be curious, excited, or terrified to meet our counterparts? Would we try to travel to other universes, or stay in our own? Would we respect the diversity and uniqueness of each universe, or try to interfere or conquer them? These are some of the philosophical and ethical questions that arise from the multiverse theory. They challenge our assumptions and beliefs about ourselves and our place in the cosmos. They also inspire us to imagine and explore the infinite possibilities that lie beyond our horizon. Parallel universes are one of the most fascinating and controversial topics in science and fiction. They open up new realms of wonder and mystery, but also new risks and dangers. They are not only a scientific inquiry, but also a creative and cultural expression. Whether they are real or not, parallel universes will continue to captivate our minds and hearts as we seek to understand the nature of reality and our role in it. Thank you for watching this video. If you enjoyed it, please like, share, and subscribe.